So we're going to start talking about chapter 5 in titled Normal Probability Distributions. But let's just remember chapter 4 was all about discrete probability distributions, where you can list the possible outcomes of a probability experiment, and right next to it you could list all their probabilities. But in chapter 5, normal probability distributions, the variable is no longer discrete. So there aren't a finite amount of listable outcomes that can happen from the probability experiment, but an infinite amount. So remember, continuous random variable is going to have an infinite number of possible values that can be represented by an interval on the real number line. For instance, how many hours do you spend studying in a day? Well, you could study anywhere between none, absolutely 0 hours, all the way up to all the hours of the day, all 24. But you could also have spent half an hour or 15 minutes or 26.2 minutes. There are an infinite amount of possibilities that we won't be able to list all off. So a continuous probability distribution differs from that of a discrete probability distribution because we won't be able to list all the possible things that can happen for a continuous variable. So how do we deal with this? Well, one way is that we look at what's called a normal distribution. Normal distribution is a continuous probability distribution. It's a specific type. Not all continuous variables are normally distributed, but it is by far the most important in all of statistics. So we're going to study the normal distribution for quite a bit. The graph of the normal distribution you may have probably seen before is called the normal curve, or sometimes called the bell curve, or the Gaussian curve after the mathematician Gauss. All right, so what are the properties of this? Well, first of all, it's a bell curve. The mean, the median, and the mode are equal. Remember, the mean is where a picture or histogram is going to balance. The median is the middle. So since it's symmetric, the balance is right at the middle. So the mean and the median are the same. You could roughly interpret the height as how often it occurs. So the mode is also right in the middle where it's the tallest. Again, it's bell-shaped. It's symmetric about the mean. If we folded this in half along that dotted line, it would all line up. So we have symmetry. The total area under the curve is 1. Now, we mentioned this in class before. What we actually are going to care about here is area under the curve between two values or above or below a value. And the area is going to be equivalent to the probability. So it's important that we learn how to calculate the areas underneath this curve. Another property of this distribution is that as the curve moves away from the middle, it approaches the x-axis, but it never really gets there. You can go infinitely far to the right or infinitely far over to the left, and it's never going to touch the x-axis. We call the x-axis a horizontal asymptote. So it will never touch. The final property is two important points. They're called inflection points. You can locate them from where the curve goes from being what we call concave up or part of a smile, like over in this region here, to part of a frown, like this region here. So where we change from being concave up to concave down are called points of inflection. If I drop a line directly below that, onto the x-axis, that will be exactly one standard deviation, in this case below the mean mu, and the other one, if we drop it down, will be exactly one standard deviation above the mean mu. So from a well-labeled normal distribution, we'll be able to get two things. We drop a line down straight from the center, and that will tell us what the mean is or what the average is for the data. And then if we can identify where the curve goes from concave up to concave down and drop down, we know that that will be one standard deviation in terms of distance away from the mean. Now, normal distribution can have any mean mu and any standard deviation sigma, but those are the only two quantities we care about. So for instance, we drop a vertical line down from the peak of this picture here, we find 3.5 to be the mean, and dropping down by the points of inflection here, we notice that it will fall down to 2. So this standard deviation looks to be about 1.5, 1.5 standard deviation with a mean of 3.5. This, on the other hand, has the same mean mu, but notice if we dropped vertical lines down from the point of inflection, it's much closer to the mean, so this has a smaller standard deviation. Now, I don't know where this drops down to, maybe a little more than 2.5. So it looks like the standard deviation is going to be less than 1 in this picture. This picture C here has the exact same standard deviation or the same amount of spread as the picture in B, but its mean has just been dropped lower. Its average is now 1.5. So if we put all that together, we'll see the means are relatively easy. We just drop a vertical line down from the peaks. The standard deviation's a little bit harder to see in terms of its exact values. Like, I didn't know this was going to be 0.7, but I could tell that this point here will drop down to something maybe a little bit more than 2.5. So it's less than 1 unit away from the average of 3.5. So it turns out to be 0.7. So those are the only two pieces of information we really need when we're looking at a normal curve or a normal distribution. We need its mean mu and standard deviation sigma. So this asks which one has a greater mean. Well, the mean is the value below the peak. So the value below A's peak is 15. The value below B's peak is 12. So obviously A has a greater mean of 15 than B, which has a mean of 12. What about standard deviation? Well, standard deviation is a measure of spread. So the more spread out something is, the greater standard deviation is. The more that it's packed together, the smaller the standard deviation. So A obviously has the smaller standard deviation, is much less spread out than B. Here's an example. We have normal distribution for the scaled test scores for New York State grade 8 math tests. We can see that the curve peaks and the line of symmetry is right about here. So if I wanted to figure out what that is, these appear to be 10, 660, 670, and halfway 675. So that's how we have the mean of about 675. Now about a standard deviation, well, this point of inflection, again, not super easy to find, but just think about going from a smile to a frown. Up right about here, we drop that down. That looks like it's just about 640, excuse me. So how far is it away from the mean? Well, 10, 20, 30 and a half, 35, just about 35. That's where we get the standard deviation of 35. So the problem starts to become, if we move back to this slide, we could say, if you recall, the empirical rule tells us that you have about, what, 68% of the data within one standard deviation. So within one standard deviation means one standard deviation below to one standard deviation above. So between these two values of, what, 640 up to about 710, the empirical rule is going to tell us that about 68% of the data is in there. So about 68% of these test scores fall between 640 and 710. But the empirical rule only works if you're dealing with whole standard deviations away from the mean. So if I went another 35 standard deviations away, or up, 10, 20, 30, and then up to here, which would be 745, that would be okay. The empirical rule will tell us this. But what the empirical rule won't tell us is, say, for instance, how many students or what percentage of the students got between a 700 and a 720. That would be between the values of 700 and 720. Or imagine the strip of area that would be created under this curve between there. And we don't know how to calculate that area. As a matter of fact, if you think about the things you know how to calculate the area of, is pretty much going to be rectangles, triangles, the things you could make out of rectangles and triangles like trapezoids or octagons, that and maybe you remember the area of a circle. But what we're looking at here aren't those. So what do? We need to calculate percentages. We want to calculate probabilities. We need to be able to calculate areas. Thankfully, every normal curve, remember, all we need to know is its mean mu and its standard deviation sigma. But any normal curve can be transformed into what is called the standard normal distribution. So let's talk about that. The standard normal distribution has a mean of 0, so the center will always be directly above 0. Well, this picture seems a little off, but this should be the center here, a 0, and a standard deviation worth 1. So below the points of inflection should be 1 unit below and 1 unit above the mean. So we know the mean is 0 and the standard deviation is 1. So we're talking about one particular normal distribution. We call this one the standard normal distribution. What's nice is any normal distribution can be transformed into this by a relatively straightforward formula called the Z formula or the standardization formula. Notice this horizontal axis is not labeled in X, but is labeled in Z. So Z is calculated by taking any X value from normally distributed data, taking any X value, subtracting from it its mean, so X minus mu. Remember, this thing is just called a deviation. And then we'll divide by a standard deviation, sigma, the standard deviation from whatever data X came from. So what Z tells us is how many standard deviations above or below average a data point X is. If X is bigger than average, then X minus mu is going to be greater than 1. Sigma is always positive. So a Z-score that is positive means that the X value we're talking about is above average. And if X is below average, X minus mu will be negative. So corresponding Z-score will be negative as well. So here's pictorially what's happening. We take, we know, let's say we know some variable X is normally distributed. So we could draw this bell curve and we know its mean mu and we know its standard deviation sigma. So we know exactly what normal distribution we're talking about. And let's just say it looks like this. Well, all we have to do is then transform each value of X that lives on this horizontal axis into a value of Z by this standard normal or the standardization formula Z here. So notice if X were mu, it means X is right at the center. Well, then I'd get mu minus mu over sigma, which is 0 over sigma. So that center becomes 0. If X was 1 standard deviation above average, say, then X would be mu plus sigma. So I'd have mu plus sigma for X, but minus mu just leaves sigma. Sigma over sigma is 1. So we see how this formula would transform any normally distributed data X into what's called standard normal distribution. What's nice about this is that we have a table of values that will be able to tell us any area that we want to know. So if I know my value of X is, I don't know, back on the test scores, 720. How many students got 720 or less? Well, 720 was above average, so it's some value up here. 720 or less means 720 or anything below it. So I'd like to know the area of 720 and below. So the standard normal distribution table is going to be able to tell us this. And for instance, we know that the cumulative area, or the area to the left of something, so cumulative area is always going to mean area to the left now, is super close to 0 for Z-scores that are negative 3.49 or less. Just think about the area to the left of this. There's not much there. So it's close to 0. And the further out Z gets this way, negative 4, negative 5, negative 6, the closer and closer the area to its left becomes 0. So remember, cumulative area is going to be area to the left. The cumulative area is going to increase as Z increases. Okay, so the total area under this curve is 1. As I start moving my Z-score up, more and more area starts to get to its left. Well, by the time I get to 0, a Z-score of 0 means you're right in the middle. So since there's symmetry in this picture, there must be 50% of the area to the left of here, and therefore 50% of the area to the right as well. But remember, cumulative area is always area to the left. Once you get up to positive 3.49, the amount of area to the left, or cumulative area, is very close to the entire thing, or very close to 1. The bigger and bigger z gets, the closer and closer the area to its left becomes 1. Okay. So the standard normal distribution table is one of the tables in your key formula sheets. It's in the back of your book as well. The way that the table is set up is that z-scores need to be calculated to 2 decimal place accuracy. So we take the z formula, z is x minus mu over sigma, and round it to the closest second decimal place, the hundredths place. And then what we do, excuse me, with the table is we break the z-score into 2 pieces. We take the ones place and the tenths place together. So 1.15 should be thought of as being composed of a 1.1 part, split it right here, and a 0.05 part. So the 1.1 part will give us a row on our standard normal distribution table, and the 0.05 part will give us a column, and we just intersect those, that row and column, and we find 0.8749. What does this mean? It means the area to the left, or the cumulative area of a z-score of 1.15, is 0.8749, or 87.49% of the total area. So this is how we're going to use the standard normal distribution table to sidestep having to actually calculate areas ourselves. Thankfully, and the table's developed by integral calculus, but thankfully somebody shared that with us. So we don't have to go learn integral calculus, which would take, a year or 2. Okay, so we take a z-score and we split it up into its whole number and tenths place, and then we take the hundredths place, intersect the row and column we get from those 2, and that gives us the area to the left. Cumulative area, area to the left. Keep that in mind. Always area to the left. So how about a z-score of negative 0.24? Well, we'll take the negative 0.2 and find that in that first column. There it is, negative 0.2, and that will generate a row of data for us. Our hundredths place is 4, so we have to find the column of 0.04, intersect those rows and columns, and we find 0.4052. So the area to the left of a z-score of negative 0.24 is going to be about 40.52%. So realize that this z-score is negative, meaning it's less than 0, so it's to the left of the center, and therefore the area to its left has to be less than 50%. So 0.4052 makes a little bit of sense. Okay, so if you want to find areas under the standard normal curve, here are the steps. Sketch a quick curve. Try to make it look a little pretty, but it doesn't have to be perfect. Okay. Then label your z-score that you want to find the area of. For this example, they're using 1.23. It doesn't really matter exactly where you put 1.23, but it's positive, so it has to be to the right of the center. So draw that line, shade that little region over here. Now you know that it's more than 50%, because we know that z-score is above 0, and the area to its left must be more than 50%. Okay. If you do look up in the table, which I suggest you do, 1.23, remember we'll split it into a 1.2, and that will give us a row on our table, and a 0.03 will give us a column. We find that area to be 0.8907, or just a little over 89% of the data. Okay. If you wanted to find the area to the right, all you have to remember is it's essentially the complement. Okay. To be less than or equal to 1.23 is the complement of being greater than it, and greater than is to the right. So the area to the right of a z-score can always be found by subtracting 1 from the area to its left. So if we find the area to the left of 1.23, and we already did that to be 0.8907, the area to its right will be 1 minus that, 1 minus that, or 0.1093. So the table only gives you area to the left. Keep that in mind. There's a little picture at the top of the table as well that indicates as such. So if we want the area to the right, you can find the area to the left of the value and subtract it from 1. Well, what if you wanted to find the area between two z-scores? Well, it's kind of straightforward. You can find the area to the left of this 1.23, which we found, I think it was like 89%, but that includes everything over here, all of this area. We only want the blue strip between these two values. So what we'll do is we'll take the area to the left of this value, which is more than we want, and then subtract the area to the left of this value. So you look up the z-scores in the table. We find the area to the left of 1.23. We already found that was 0.8907. Excuse me. If you look up negative 0.75 on the table, you'll find its area is 0.2266. We'll simply subtract 0.8907 minus 0.2266, and there gives us the area of a strip. So now we can find the area to the left of a value, the area to the right of a value, and the area between two values. So just an example. Find the area to the left of negative 0.99. So we have to look up negative 0.99 on the table. We find it to be 0.1611. Straightforward, done. What about to the right of 1.06? We'll find the area to the left in the table, excuse me, which is 0.8554, subtracted from 1. And now you have the area to the right. Area between, give this one a try yourselves. Pause this, whatever you want to do. Find the area to the left of a 1.25 first. That'll give us the blue area and this extra little tail, and then find the area to the left of this, which is the tail, and then subtract the 2. Again, relatively straightforward. Make sure you get comfortable with this. Okay, so that's section 5.1. We want to interpret the graphs and understand normal probability distributions and finding areas to the left, to the right, or in between two different z-scores in the standard normal. Okay. Well, if you got any questions, feel free to email me.